All right, so today is April 22nd. I just put in the grades for a quiz and they were low, so I'm doing a review video. I actually mistakenly did another review video, so there's already a review video for the quiz you just took today. There we go. So this quiz was a little while back. It was mostly on inscribed angles. And there was some stuff on tangents as well. So inscribed angles and tangents. I'm just going to go through all the lesson stuff super fast. All right, so we did inscribed angles, the number one concept, really the only concept. If we have an angle and the vertex, so the vertex, the pointy part of the angle, is on the circle. So that's the angle right there. So the angle, the measure of the angle would be that part in there. Or if we look at a bigger picture there, that would be the angle in there. So there's the vertex. Again, the vertex is on the circle for all of these. The measure of the angle, so this part in here is equal to 1/2 the arc times the arc. And when we say the arc, it's the arc that's inside of the angle. I'll show you what that means. So 1/2 times the arc. So this is the arc. This is the arc that is in that angle. And the arc that is, it says intercepted if you read the theorems, but it's just kind of the part of the circle or the arc that is inside the angle. So the reverse math then, if I knew the angle, again, so this is if I knew the arc, I would take 1/2 of the arc. So if that was, guessing, not 90, maybe 70. That was a 70-degree arc. Well, then the angle would be 1/2 of that. 1/2 is the same as dividing by 2. So the angle would be 1/2 of that arc, so about 35 degrees. And they're always in degrees. Well, the opposite math and the opposite formula would be, well, what if I knew the angle and not the arc? And I wanted to find the arc. So let's say, again, just do the same numbers. So if that was 35 degrees, and I wanted to find the arc, I would have to multiply it times 2. 70 degrees. Okay, that's the relationship. Angle, the measure of the angle equals the arc divided by 2. And if we multiply both sides by 2, then we get that the arc is equal to 2 times the angle. So again, inscribed angle, that's the part you got to recognize. Vertex is on the circle, and then there's the angle, and the arc we're talking about is the part inside that angle. All right, so there's your concept. That's pretty much everything you need to know. There was some other theorems. So here's another theorem. If you want to memorize all of these, you can. I did not teach it that way, though. I taught you that one concept, and then we solved everything using that one concept. So that's the way I'm going to do all the problems. Hold on, I got to zoom out. Yeah, there we go. So where's the other theorems? So here were the other two theorems down here then. Just one theorem, I guess. No, what's the other theorem? Shoot. 16. Oh, here it is done. All right. Actually, I'm just going to do this. Hopefully this works. Oh, that's as much as I can zoom in apparently there. So I guess we got to zoom in here. All right, so inscribed polygon. So that's this figure right here. If we have an inscribed polygon, that just means that the polygon, which is a shape that has straight sides, basically at least 3 sides, the polygon is inside the circle. So that's what inscribed means. It is inside the circle, and all of the vertices are on the circle, because that's what inscribed means. We just did that a second ago with angles. Inscribed angle means the vertex is on the circle. So that is an inscribed angle. So this triangle is really just, it's 3 inscribed angles, is really all it is. And it just so happens that we're connecting them all and making a triangle. So there's one angle there, and then I could do red. There's another angle there, and then the last angle would be this angle here. So again, it's really just 3 angles. It's just that it's all connected, so it looks like one shape. So again, just think of it as a bunch of inscribed angles, just like what we did right here. Just if we connected that and made another one, there we go. We just created the same figure. So if that's the case, all of these angles, again, I'm teaching it a little bit differently. That angle there is half of that arc. Well, if we look at the picture, we know what this arc is. The arc is 180 degrees because we know FH, and I think it probably tells us that. Yeah, right there. We know FH is the diameter. And we also know because it goes through the center of the circle and it has points that are on the circle. So we know that has to be a diameter. So anytime you make an angle out of the diameter, so you use the F and the H as the endpoints, that has to be a 90-degree angle because like we just said, the inscribed angle, G is on the circle. That's what makes it an inscribed angle. The inscribed angle is half the arc, and we just said, well, we know that the arc is 180 degrees. So half of 180 is 90. So I did this in class, I believe, and I drew a bunch of lines in. I said, well, what if I do from there to there, and from there to there? That wasn't perfect, but that's fine. Well, again, if the arc is always going to be this arc up here, which it is, so that arc is always going to be 180 degrees. Every time I draw lines in, so I can do this with highlighter. So if I draw in from here to here, and then from here to here, well, again, that's got to be 90 degrees because the arc is 180. That yellow arc is still the arc associated with those green lines. We do it again. Let's do it in blue. So if I draw in from here to here, and then from here to here, well, again, that arc associated with those blue lines is the yellow arc. Well, if I know that yellow arc is 180, then that inscribed angle has to be 90. So every time you draw an angle in, and the endpoints of the angle, basically the diameter, this line is the diameter, well, then the arc is always 180. So that yellow line is always going to be the arc. And therefore, the inscribed angle, every time you draw it in, the inscribed angle has to be a 90-degree angle. That's what that theorem says. So again, you can memorize that theorem and just know every time you see a diameter and you see that there's a triangle drawn in, an inscribed triangle drawn in using the diameter, well, then it has to be a right triangle. Yeah. So anytime you draw in a figure like that, you're always going to create a right angle, which means you're always going to create a right triangle, which means this is going to come into play. Potentially. if you're talking about the length of the sides. So a squared, b squared, c squared could come into play. Let's see. So we'll do some problems instead. Actually, I don't know if I'm gonna do a bunch of problems because I want to keep it short. So here we go. If we know this is the diameter, well, this is an inscribed angle. So I know the arc on the other side has to be 180. So that's 180. Well, if I know that's 180, this inscribed angle has to be half of that. So that is 90. Well, that means this measure. So this is the measure of angle M. This is the measure of angle K. And then this we know is the measure of L, which is 90. I know all three of those added up have to be 180 because all the angles of the triangle add up to 180, all the interior. So that would be my equation to solving that. A lot of people on the quiz just did what you guys tend to do, and you just set them equal. They are not equal. So don't think that they're equal. You have to understand the concept that we just went through. You could have just added them together and set them equal to 90 because mathematically, when I subtract the 90 and subtract the 90, that's what I would get. So 5x subtract 4 plus 8x subtract 10 equals 90. So that equation was fine. But it's not just, that is not a situation where you can just set them equal to each other and be correct. They're not equal to each other. Let's see, next example. So that's an inscribed angle. That is a diameter. So anytime I create an inscribed angle, again, the arc here is 180. Well, then that means that is 90. So same concept that I just went through a second. You could add all three of those up. This one plus this one plus this one equal 180. So this is the next theorem. Oh boy, I gotta go up. So the next theorem. Hold on, I have to zoom out. I think it's on. I think I have to go left and right on this one. Zoom way. Let's see. There we go. So I'll try to zoom in as possible. And so that's as much as I can zoom in there. So again, there's a theorem you can memorize. If you want to just memorize that whole theorem, you can. Anytime you see this picture right here, you can just say, okay, yeah, that's that theorem I memorized. I'm going to try to teach it to you a different way. This is basically just inscribed angles. That's an inscribed angle. That's an inscribed. Actually, let's do it in bright color. That's an inscribed angle there. This is an inscribed angle here. Try to like trace outside it. So that is an inscribed angle there. And then this is an inscribed angle here. Again, now there's no diameters. There's no other information that it's not a parallelogram. A lot of kids maybe thought it was a parallelogram. It's not a parallelogram. We don't know anything about any lines being parallel. So all we know is we could say there's 360 degrees in all the angles, because anytime we have a four-sided figure, we can draw a line through it. I mean, this is old stuff. We know all triangles are 180 degrees, all the angles at least. So that means if I have 180 and 180, we said all four-sided figures, all quadrilaterals, their internal angles add up to 360. So we know four-sided figures make up 360. So we could say that, but again, that doesn't really always help us. So here's what we did. I'm going to go to the other page for this to make a larger figure. So if we have a circle, and let's say we draw in a four-sided figure. There's our four-sided figure. Again, not symmetrical. I don't know that there's this, you can't say this line down here is a diameter. I have no idea if that's a diameter or not, so don't think you can say that's the diameter. Even though it kind of looks like it could be, probably not. It looks a tiny bit too high, but I don't know anything. Absolutely nothing I can say about that other than the fact that I have a four-sided figure. Just erase that. It does erase that. No, it didn't. Huh. Well, that's pretty weird. Let me draw that anyway. It's great when I use the tool to draw a line in. Erasing. All right, so there's my figure. So what I could say is, well, let's think about angles. I know this angle right here is associated with this arc right here. And I mean, the way I know that is if I just follow the angle out. Okay, so I just follow the angle out. Well, here's my endpoint. Here's my endpoint. So that blue arc is associated with the angle. So this angle is 1/2 of this arc. Or you could do it the other way around. The arc is twice the angle. Again, I know that. Let's think about this opposite angle. Here's the opposite angle here. No, I'm sorry, the opposite vertex technically, but the opposite angle would be this angle. Nope. That's the angle. Well, isn't that weird? They share the same endpoints. That angle has the same endpoints, which means this arc is the arc associated with that red angle. So this red angle here is associated with this big red arc. Well, then we know this angle is 1/2 times the big red arc. Again, that's just going back to inscribed angles. Well, if you'll notice, my arcs cover the whole circle. Right? The blue line, the blue arc, and then this big red arc take up the whole circle. So I know the arcs have a total degrees of 360. Well, I know that the angles that I'm talking about, so that red angle there and this blue angle down here, we said are 1/2 of the arcs. Well, if the arcs take up 360 degrees, and if I take up, or if I know that the angles are 1/2 of the arcs, then the two angles added together would have to be 180 degrees because they're 1/2 of the arcs. Again, individually, I said this blue one is 1/2 the arc. I said the red one is 1/2 its arc. Well, then that means they're both 1/2 of 360 because that's the blue plus the red arcs. So that means the angles have to be 180. So the theorem says, so again, if you don't get that, you can memorize. My computer or my projector screen actually is not. Oh, king of court. Oh man. I don't know where that is. Hold on. Now I gotta zoom way out, try to find the correct page. King of the court. You weren't here. Mr. Gill was king of the court when we played the tennis team. There. All right. So that's it was just showing me the top part of the interest. So the theorem that we went over said, there we go. Opposite angles of a quadrilateral, so that's the key, that is inscribed, so the quadrilateral is in the circle. So you can see there's the quadrilateral. It is inscribed, meaning all of these are inscribed angles. Said that opposite angles, so M plus K, have to add up to 180 degrees, or L plus N have to add up to 180 degrees. And that's the angles. Angle, angle, angle. So that's what the theorem says. You can just memorize it, or if you followed what I did a second ago, you'd be able to figure it out. Just understand how inscribed angles and arcs work. I'm not going to do constructions on this video. If you want to, you can go back and watch the full video for construction stuff. Let's see. I think that's it from this chapter. Yeah, because the problems, yeah, this was the last example, which has to do with what we just did. If you'll notice, and this triangle didn't even come into play. That didn't even come into play. If that right there is a quadrilateral four-sided figure that is inscribed in the circle. This here would be a right angle right there, because that's a semicircle that's 180, and that's an inscribed angle, so half of the 180. That's how you do those. Let's go into the tangents. Oh, really quickly, I do want to show you this. If you're really struggling still to figure out how angles match up with arcs, it should be easy to match the angle with its arc. You just go and you trace the angle lines all the way to the other end of the circle. Just trace them all the way out. So for angle QGO, the arc that it intercepts is just QO. It's just from the two endpoints is the arc that is intercepted. It's a little trickier to go backwards and say from the arc, what is the angle? So let's say I wanted to do arc GR. What angle, or it could be multiple angles, could share an arc, remember? You have to trace the lines back. Do this with, so trace the line. So from point G, I'm just going to pick a line, trace it to the other end of the circle. Now I try to go from point O to point R. Well, there's a line that goes from point O to point R. So that angle matches up with arc GR. Arc GR matches up with angle, what is that? GOR. Now, don't stop because there could be other angles. Now, this one doesn't have a ton of lines. So I'm going to do in, let's see, we'll do it in purple. So now I take this line here. Now, is there a line that goes to R? No, there's not a line to go to R. So that's the only ones that match up with arc GR. The only angle is GOR. Let's do one that does have two really quickly. So if I wanted to go to arc PN, so what angles match up with arc PN? Again, here's the arc. So I go from angle P, I take a line, I trace it out. Can I get back to angle N? Yes, I can. So there's one angle right there. PEN works. Angle PEN matches up with arc PN. Nope, I know. What about this line? I go all the way down here. Can I get to angle N? Well, sure enough, I can. So there's multiple angles already. So we'll say, what is that? PFN works. That's another angle that matches up with arc PN. Then I just keep going. So next one, I go down here. Is there a line that goes to N? No. So that doesn't work. So I can skip to the next line. Well, this goes straight to PN, so there's no way I can make an angle at all because there's not. That's just a straight line. So these are the only two angles that match up with arc PN. So again, just trace the lines. Tangents, quickly. So a line that touches a circle at only one point is called a tangent. If I have a circle, I have a line, and if I take that line and if I drag it slowly, and eventually it's going to hit just one point. There's going to be one point of that circle that is the farthest out. And when I hit just that one point, it's visually impossible to even show. So visually, you could never draw small enough to do it. Can't even move it correctly. So visually, you can't do it, but the point is, it hits one spot. So the only spot that line touches is right there on the circle. It doesn't touch any other points on the circle. That's called a tangent. And the tangent line has a very specific property. We said that is the number one thing we have to know. If I draw in a line that is either a radius or a diameter, could be either, because basically a radius is just a diameter shortened, or a diameter is just the radius that is lengthened all the way across. The only way that the diameter or the radius can intersect a tangent line at the point of tangency, so this guy right here, that one point called the point of tangency, it's in your book. So the only way they can intersect right there is if they are at a 90-degree angle, if they're perpendicular. That has to be the case. A radius or diameter that intersects the tangent line at the point of tangency. It does have to be at the point of tangency, but that pretty much is always what it's going to work. That has to be a 90-degree angle. So what's going to happen, you haven't guessed, we're going to again get some a squared plus b squared equals c squared problems. Because if I connect the line down here, I've now created a right triangle, and we know for a right triangle, this is true about the sides of a right triangle. So a lot of the problems revolved around that. Oh, there was a problem just like this. If we know all of the sides of a triangle like that, and if we're trying to determine whether or not that is tangent, the only way it can be tangent, man. The only way this line can be tangent, because we see this is a radius, so if we know that's a radius, that has to be a 90-degree angle. That's just by definition. Tangent has to be perpendicular to the radius. Well, I just have to determine then, is that a right angle? Is that a right angle? Well, so again, it's a little bit backwards, but the only way to determine that is to do a squared, b squared, c squared. Now there's one little tricky part here, because my hypotenuse should be across from the right angle, but then a lot of kids are saying, well, wait a minute, how can the hypotenuse be the shortest side? It's not. The way you read these figures is you have to understand this 6 only goes to that section right there. This section here is a radius. So it's 9, just like this one is 9 down here. So when you plug in the values, it would actually be 9 squared plus 12 squared equals 15 squared. And if you do the math, that is a right triangle. You get 225 equals 225, I believe, which means, yes, that is tangent. If it is a right triangle, which it is, that makes this a right angle, which means that is a tangent line. Otherwise, it would not be a right angle. So there were a couple of problems revolving around that concept. And one of them you had to solve. It told you it was a tangent line. So then you just had to use a squared, b squared, c squared to solve. And then in another problem, you had to determine whether or not the line was tangent. And you did that by just determining whether or not the left side equaled the right side when you did a squared, b squared, c squared. Let me zoom way out. Try to find the next thing. No. So again, here's a problem. That problem right there on 228, I think, is the next kind of example that I just mentioned. Oh, here, there's only one thing you really need to know here. I'm not even going to do the problem because most people guess it correctly anyway, or at least they guess the equation. If we have two tangent lines, did I go over this? I skipped it. Hold on, I got to find this theorem real quick. Oh, yeah, it's over. Where is it? I may just do the theorem for you. For huh. Oh, here it is up here, way up here. So there, totally skipped over it. Yeah, so this is the only other concept. If you have two tangent lines coming out of the same point outside of the circle. So you see down here. So this is a point outside the circle, and they tell us in the problem, those two lines are tangent. Well, the theorem says these two lines are congruent. There's not a great intuitive way. I mean, we could do a proof probably, and this would be an isosceles. Well, actually, you wouldn't know it was an isosceles triangle yet. So we didn't really do any proof for it in class. We just said, just think about it. In order for this line to be the like tangent to that side, like you would have to be kind of in the middle of this circle. Like you'd have to be right in the middle if those two lines were going to be tangent from the same point. And then we may have just said memorize it. I can't think of anything else that we said. The reason I didn't worry too much about it is because you guys normally guess if you have two little mini equations, you normally just guess that you set them equal. And in this case, that's correct. That's why I didn't spend a ton of time on it. But yeah, we definitely didn't do a proof on it. So that's one you just need to memorize. Two tangent lines coming from a point outside the circle are congruent. So the equation would just be 7x subtract 9 equals 5x plus 5. So we could also make other shapes from this. Oops. Like we might draw in another line or have another point that's tangent. So if you'll notice, we sort of actually, there would be even technically another point. Like there. So there, now we got a bunch of tangent lines. So I've got two tangent lines here coming in. So these two red lines would be congruent. These two green lines, if that's tangent, oh, that's not good. If that line is tangent and that line is tangent, those are congruent. And then the two blue lines below would be tangent. This blue line would be tangent to this blue line here. So you can have a shape that is circumscribed around a circle, and it's really just a bunch of tangent lines that are just all equal to each other. So these two would be equal, these two would be equal to each other, these two will be equal to each other. So there's some problems that we did recently like that. So this is kind of where that originally started. So it gets into that a little bit right here. That just means we got a bunch of congruent lines. Those two are congruent. Those two are congruent. And those two are congruent there because they're all tangent lines that are coming from one point outside the circle. So the last theorem, I don't even know if I put this on the quiz, I don't remember, but this particular theorem right here, again, you can memorize it if you want, or this one's not too bad to understand. If I know we have two tangent lines, so I know that is tangent and I know that is tangent. Well, I also know that's a radius and that's a radius. So the number one concept, I said this a million times and you guys didn't write it down and it made me so mad because I said this is the number one thing you got to know. And then next class, nobody knew. So write it down right now if you're watching the video. That has to be a right angle. If the two blue lines are tangents and the two red lines are radiuses, the number one concept is that those form right angles. They're perpendicular to each other. So now using some of our old stuff, if I know every four-sided figure has 360 degrees, oh, my board's really messing up. I know this figure, PRSQ. I know that is a 360 degree figure, or the angles, the interior angles add up to 360. Well, if I know, oh man, my board just really straight. If I know that angle right there is 90, that angle right there is 90, then that means that P, angle P, plus angle S have to also add up to 180. Here, I'm gonna write some notes. So again, this is, let me hear. So if I know Q plus R is 180, then I know angle P, oh yeah. Oh boy, this is really, oh, angle, I give up. So angle P plus angle X, S. So again, down here, just draw an arrow to it. Angle P plus angle S has to be 180. Because Q plus R is 180, and I know the whole figure has to be 360. So therefore, if I subtract 180 out of it, there's 180 left, which means P plus S. Wow, I'm trying. Cool. There, it's a little better. So angle P plus angle S has to equal 180. That's what this theorem says right here. But again, it's just because we have two right angles. So if you subtract those two added away from a 360 degree figure, then you're left with 180 for angle P and angle S. All right, so that was the last concept. These were the problems you had to do for, it was the quiz. The due date will be, I think it's May 2nd. That'll be the last day. But I believe you took it on 20, no, not the, yeah, the 22nd. I think you took it on April 27th. So again, those are the problems for that quiz that I just did. Make sure you go to tutoring if you owe me tutoring. A few people have been trying to show up without tutoring, and I've said, no, you cannot take the quiz. The retake. You can always make one.